In this video, we're going to take a look at the first possibility from Le Chatelier's principle. So this is an example of Le Chatelier's principle. And this is where we add a strong acid. And again, you really don't have to necessarily think of this as a totally different problem. It just comes down to how we fill out the ice table. So what we have here is we have formic acid and it's mixed with some HCl. So let's write down some of our reactions that are going to be taking place as things go on. So the HCl is the first one that we'll kind of tackle, and that's because we know that when we put HCl into water, that's going to go 100% to products. It's going to make H3O plus and Cl minus aqueous. And so if we have 0.2 molar HCl, we're going to have 0.20 molar H3O plus present in the solution. And so this happens automatically and quantitatively immediately as you put the HCl in. And so then how is that going to affect our formic acid? Well, our formic acid, when that's in solution, HCHO2 aqueous, this is going to have the water around also. And so this is going to be in equilibrium with H3O plus aqueous plus the formate anion. And so now the question is what is this H3O plus going to do to our reaction? Well, this H3O plus, the way that you can kind of think of that is when we add H3O plus to the solution, that's going to pump up our H3O plus concentration on the right and push our equilibrium back to the left. So what we're going to get is we're going to get a slightly lower concentration of the CHO2 minus, and we're going to get a slightly higher concentration of the CHO2 aqueous solution that we would have than we would have if we just had this formic acid by itself. So let's work on how we can solve this with the ice table. So first thing I'm going to also do is I'm going to write my Ka equation, which is that Ka is equal to the concentration of H3O plus times the concentration of the formate anion divided by the concentration of the formic acid. And so for our ice table, we know that we're starting out with 0.10 molar formic acid, but the interesting thing in this case is that our H3O plus is not going to be 0. Our H3O plus is going to be starting with a value of 0.20 molar. And this is what we had said when we were talking back conceptually about this. We said that the strong acid is strong. So it's going to first control the pH, meaning all of it is going to dissolve and break up into H3O plus. So the H3O plus concentration is going to depend on that strong acid. And so it makes sense that this is going to appear as an initial condition because we have that hanging around from the strong acid. And so our formic acid hasn't broken up yet at all, so we're going to have 0 molar of the conjugate base. But this is coming from the strong acid, the 0.20 molar. So what we're going to get here is we're going to get a little bit of the, under these conditions, the formic acid is going to break up. So we're going to lose a little bit of the formic acid, and we're going to gain a little bit of H3O plus, and we're going to gain a little bit of the acetate, of the formate anion. So we're going to get 0.10 molar minus X, 0.20 molar plus X, and X. And so we can bring that over and plug that into our Ka expression. We have 1.7 times 10 to the minus 4 is equal to the concentration of H3O plus, which is 0.20 molar plus X, times X divided by 0.10 molar minus X. And so this is looking kind of ugly, and you're probably saying to yourself, gee, this is not the greatest thing to have to solve. But we can do our approximation, and we can check. So in this case, we have 0.20 molar and 0.10 molar. So we're going to kind of check them both. So we're going to take 0.20 divided by 1.7 times 10 to the minus 4, and we're going to do 0.10 divided by 1.7 times 10 to the minus 4. And we're going to see if both of those are greater than 100. And it turns out that they both are. So if they both are, we can actually go in and delete these x's that are being subtracted, because what we're saying is that those x's are going to be so small relative to those concentrations that it's not really going to make a difference. Effectively, within significant figures, it's going to be equivalent. And so this simplifies to a very, very simple equation, where now all we have to do is divide 0.20 by 0.10, and just bring that over to the other side and do our division. And so when you do that, you get X is equal to 8.5 times 10 to the minus 5 molar. And so this is going to be our concentration, and so this is going to equal our concentration of the CHO2 minus, which is the answer to the question. Now, one interesting thing that I want to point out is if you calculate the pH of this, if you take 0.20 molar and you add that amount to it, if you take 0.20 molar plus 0.000085, what you're getting is you're getting 0.20 molar. So that's just to show you that the approximation works. But what's really important is that the pH, which is equal to the negative log of the H3O plus concentration, in this case, is controlled by the strong acid. So the fact that we put the strong acid in means that regardless of what's going on with our weak acid and base stuff, that pH is going to be locked in by that strong acid. And that makes sense because strong acids are strong and they're gonna fully ionize. The weak acid is weak, and that's going to have a much lower impact on the, relatively lower impact on the H3O plus concentration. So you'll notice that if you were to calculate the pH of this one, you would get the same pH as you would get in just a solution of 0.20 molar H3O plus.